All right. Good morning, folks. Well, welcome back. Hopefully, you had a nice day yesterday. Just a quick note: I posted the chapter 14 material for you. I apologize for the chapter 13 material. I forgot to post the homework for you, but this time I posted everything for you. My hope is that we can go ahead and get started with chapter 14 on Friday. Hopefully, on a Friday. We'll try to wrap up this chapter tomorrow. And then I'd like to meet, let's try to get a Zoom meeting. I'm going to try to schedule a Zoom meeting for next week. I'll let you know how that's proceeding. So we'll go ahead, and I'd like to meet to see if you have any questions, see how you folks are doing with the work. Okay. And then remember, the next exam is going to be at the end of chapter 14. I'll combine together the chapter 13, 14 material for the next exam. And then, but like I said, that won't be till the end of chapter 14. Okay. And so start taking a look at chapter 14, folks. What I'd like to do today is I want to finish up with our general discussion of gases here. We'll talk about that, and I would like, and we'll get started with the liquids. My hope is that we can try to get done with the liquids by tomorrow and start the solids on Thursday. We can get started with the chapter 14 on Friday. Okay. I think the bulk of this chapter is going to be probably more focused on the gases and the liquids. And like I had pointed out to you when we started this chapter, the gases here, the general discussion of gases that we're having right here, is going to be very important for you as we move into chapter 14. So make sure you keep in mind, if you have to review the section of chapter 13, okay, before we start chapter 14. But like I said, we're going to move on, and we need to discuss the remaining two states. And the key in understanding what we're doing here, folks, and I think I've been trying to emphasize this point to you from day one in our classes, that in science in general, and chemistry in particular here, we need to be able to make the connections between what we can observe on the macroscopic level, and that is all of the phenomenon that we can observe on the macroscopic level. You need to be able to account for those that behavior. We need to account for those observations by trying to explain those observations, by trying to explain it on a microscopic level, trying to explain how things work, explain how those observations come about on a microscopic level. That is, how do the particles behave? How do molecules, how do atoms behave to account then for what we can observe on a macroscopic level? And I think that's true of all science, again, whether it's physical sciences or biological sciences, that has to be true. And so we've been really emphasizing that point during this chapter here, where we're trying to explain then the one property of gases that we can, for the most part, always experience and observe, and that's the pressure that gases exert. Okay, and so we can explain that gas pressure based upon the motion of the gas particles, and how they interact with everything around them by pushing and bumping in, colliding into everything. We talked about how we can change that pressure by changing variables such as how much of the gases we have, the mass of the gas. So we have more gases, the pressure will be greater. We have less gases, the pressure will be lower. Then we talked about how we can speed up the gases, give it more energy, and that kinetic energy we saw then was directly related to the heat energy, which we can measure and which we can observe by using a thermometer, and thus measure its temperature. Right. So make sure then that we're trying to make that connection. And as we go on and we talk about liquids, I'm going to further that discussion about the connection between microscopic behavior and what we can observe. And that's going to be critical for you to understand certain properties of liquids, such as, say, vapor pressure, or we don't talk about it in this class, but adhesion and cohesion, boiling point, and so forth. So liquids present us with a whole lot of interesting properties that we can observe. And we interact with liquids, that interaction is much more noticeable than the interactions we have with gases. Okay, so gas interaction is much more subtle. Okay, now if there's great changes in pressure, then we notice it fairly well. Like we saw that if you change altitude, if you go up in altitude, if you go up higher in altitude, we know that the gas pressure has changed because we can feel it. So that interaction is not subtle. But as long as we're here at sea level here, the interactions with gases are fairly subtle. Okay. Now, obviously, we don't have certain gases, we don't continue living. So that's not that's pretty dramatic. But the point though is that we don't notice the presence of the gases, but we do notice the presence of the liquids. Okay, we do notice how we can interact with it, and so when we get to liquids, we'll talk about that. Okay. All right. So where we left off with yesterday then was, and what you want to make sure you keep in mind then is that there is a direct correlation. There's a direct connection between the motion of the gases, which we can measure in terms of the kinetic energy of the gas. Okay, so which is related to this kinetic energy that we talked about, and the temperature. Okay, so the average kinetic energy, which we talked about here, and we use the term average from here on out. When I use the term kinetic energy, when anyone uses the term kinetic energy, we're talking about the average kinetic energy of all these particles together. Because we saw yesterday in those graphs that at any given temperature, that at any given moment, that you have a certain number of gas particles that are moving slower than everyone else, a certain number of gas particles that are moving faster than anyone else, but the bulk of the gas particles are moving at a mid-range speed, at that given temperature. Okay, and so with that said, then make sure you keep in mind that when we refer to kinetic energy, we're referring to how fast the gas particle is moving as well. Okay, so that the speed of those gas particles are dependent, or the speed is dependent on the temperature, the heat energy. So as you increase the temperature, you increase the heat energy, you increase the speed at which the gas particles move. And so what happens to the pressure? Well, as you increase the speed, as these gas particles move faster and faster, they will collide with each other more and more. And it's those collisions then that will lead to the increase in pressure. And so I'll try to summarize things up for you towards the end here, but make sure you keep in mind that we're trying to develop a link now between temperature and gas pressure itself. We can measure the temperature of the gas and we can measure the pressure of the gas. Both of those are observable quantities that we can now connect. We can see then the relationship between temperature and pressure, and that is important. You got to make sure you keep that in mind, because we will talk about those relationships between, for example, temperature and pressure, between volume and pressure, and number of particles and pressure, and that's going to be the primary focus in chapter 14, where we will develop equations and we'll do the math that relates all those properties to one another of a gas. Okay. All right, so here we're focusing on the average kinetic energy of a gas and its temperature. But I went further and I pointed out to you then that the average kinetic energy of a sample of a substance will be the same regardless of what state it's in. The average kinetic energy at a given temperature, the average kinetic energy at a given temperature will be always the same regardless of the physical state. And so we talked about what was called this triple point yesterday, okay, and we'll talk about more about triple points towards the end of this chapter, okay, when we talk about physical phase diagrams, okay. All right, so at this point called the triple point, and the triple point is essentially a temperature. So here we have a temperature, the temperature, okay, so this is measured in 0 degrees Celsius temperature, and a pressure, okay, at which all three states exist. Okay, so at the triple point then, it's a temperature and pressure at which all three states exist. Here I give you the temperature for water, so we're looking at water here, okay. So the triple point of water then, at this triple point, at the temperature of 0 degrees Celsius, roughly 0 degrees Celsius, and 1 atmosphere. So it's going to be 0 degrees Celsius and roughly 1 atmosphere. Okay, at this point here, okay, and a little less than 1 atmosphere. At this point here, we see then that all three states of water exist. All three states of water exist. Okay, we will have then the solid state. Okay, so we'll, if you notice, and this is a sample here of water in its triple state, at its triple point. Okay, we'll have then the gas here. You can, I'm sorry, the solid here. Sorry. You kind of see the ice forming right here. Okay, the solid here. Okay. We obviously have the liquid here. Okay, so the liquid. Okay. And just above here, which you don't see then, we have the water vapors. Okay. So we have all three states existing at 0 degrees Celsius. Okay, so 0 degrees, 0 degrees Celsius. Okay, and at about roughly 1 atmosphere. Okay, so at this point, then all of these particles, whether it's in the solid state, the liquid, the gas state, or the liquid state here, all these particles floating around here have the same kinetic energy. Remember, the speed of these particles, the kinetic energy of these particles, okay, will be dependent on the temperature here, not on their physical state. So the solid particles that are moving around here, even though they're packed really close together, and we'll talk about how solid particles move hopefully tomorrow. These gas particles here, as they're moving around in a random, rapid manner, and these liquid particles, as they also move around in a random, but not quite as fast, a random and rapid manner as well. They are all moving at the same speed, okay? And that's what you need to make sure to keep in mind. So the physical state of a given substance does not determine it's the speed of the particles. It is the temperature that determines the speed of these particles, okay? All right, good. So make sure you keep that in mind. And so with that said, then, if that's the case, then we can determine then, we can make this connection between the average kinetic energy and temperature. But the connection between the average kinetic energy and the Kelvin temperature scale. Now remember, there's two different temperature scales that we will deal with. We don't deal with the Fahrenheit. Okay? We have the Celsius temperature scale and the Kelvin temperature scale. So we have two temperature scales here. And remember, the relationship between these two scales is 273. So we can convert to one scale and another. Okay, so for example, then 0 degrees Celsius, which is the freezing point of water, represents then 273 Kelvin. Okay, so there 0 degrees Celsius. Okay? So therefore, there is a relationship between these two that is fairly direct, but the relationship between the kinetic energy and temperature is a direct one when it comes to the Kelvin scale. Not so much with the degrees Celsius scale, but the Kelvin scale. Why is that? Okay, because of one very simple fact, and that is that when we talk about absolute zero, okay, absolute zero represents then a temperature that is 0 Kelvin. Absolute zero is 0 Kelvin, not 0 degrees Celsius. If we wanted to measure that in degrees Celsius, it would be negative 273 Celsius. And so that's why we've chosen the Kelvin scale to make this connection. And so the link here is between the Kelvin scale and motion, okay, and kinetic energy. Okay? And so when we take a look at this, then when we take a look at this relationship here, okay, we can take advantage of the fact then that all motion ceases, all motion stops when we are at 0 Kelvin. And so that's why we can make this connection, and it's a direct connection between the temperature here, and the motion here. So if all motion stops, then if all motion stops at this point, okay, we can then say that there's a direct relationship between the Kelvin scale, between the Kelvin temperature scale, between the Kelvin temperature scale and kinetic energy. And so the way we represent that then is using the relationship here. We were saying then that whenever we have a certain temperature in the Kelvin scale, we can directly relate it to the kinetic energy. Okay. So that's something that we want to take advantage of here. So for example, let's go ahead and take a look at an example here. Okay. Let's take a look at an example here. Okay. So we start out then, we start out with gas here at a certain temperature. So at a certain temperature, about 200 Kelvin. So that's the temperature scale there. Okay. And then we take a measurement of the energy. Okay. We can do this using a process known as calorimetry if we wanted to, but we can measure the energy here. And then we say then that the energy of the gas particles as they move around here is about 500 joules. So this is the kinetic energy. So the unit of joules here tells us this is kinetic energy. Okay. And this is temperature. And again, temperature, if I want, again, I want to draw your attention to this in Kelvin. Okay. So we can use this to determine then how fast these gas particles are moving. Remember, because if we know what the kinetic energy is, okay, And if we know what the mass is of these gas particles, we can find then out how fast they're moving. Okay, so with that said, then, but we don't need to do that at this level here. So what we want to be able to do then is we want to relate kinetic energy to the temperature and the change. Right, so we initially have these gas particles moving at a certain speed, at a certain kinetic energy, and then we will start heating it up, which means then we are adding heat. So we are adding heat energy, and we already saw this relationship. As we add heat energy into these gas particles, the kinetic energy will increase. So as we increase heat, which is me, and we can measure that by increasing the temperature. As we increase heat, then that leads to an increase in the kinetic energy of these gas particles. Okay? And if we have an increase, and we talked about this as we increase the kinetic energy, the speed of these gas particles will get faster as well. Okay, so make sure you continue to keep this in mind right here, what I've written for you down at the bottom here. Okay, so if we increase the heat, we add in heat into this. Okay, we add heat into this chamber here. These gas particles will absorb that heat energy, and they will start to speed up. And as they start to speed up, they're going to collide with the thermometer here more. Okay, and so we will notice then that there will be an increase in the temperature. So let's go ahead and let's consider what we have here. So if we increase in heat, okay, we will increase the temperature. Okay, so let's say we increase the temperature to 400 Kelvin. Okay, so we add enough heat. We read the temperature, we read the thermometer here. We read the thermometer here. So we start out here at 200 Kelvin, and then we double the temperature. We add enough heat to double the temperature, and so we measure that. Okay, we measure that. Now, without having to measure the kinetic energy. Okay, so we have the kinetic energy here. Without having to measure the kinetic energy, we can actually estimate the kinetic energy right here. So if we double the temperature, okay, what you'll make sure you understand is that there's a direct relationship between the Kelvin scale and the energy, the kinetic energy. What we can say then is that the energy should double, and actually, effectively, it does. So if we were to measure it, the kinetic energy now will rise to about 100 joules itself. So the energy doubles. So if we can measure the temperature in Kelvin and determine then how much increase or decreases, we can correlate that to the increase or decrease of the kinetic energy as well. So we don't have to measure it again. Okay, but then again, like I said, the relationship is directly between the temperature scale and the kinetic energy, the temperature scale in Kelvin and the kinetic energy scale and the kinetic energy. Now, mind you, as you increase the temperature, whether it's in degrees Celsius or in degree or Kelvin, okay, the kinetic energy will always increase. And so that's why I draw your attention back to here then, folks. And so let's go back here and take a look at this. This is what you need to make sure you remember that, okay? Now, take advantage of the relationship between the Kelvin scale and energy, but this is what you'll need to remember as you move forward, and that is there's a direct relationship between heat energy and kinetic energy. And we can measure heat energy. We can measure heat energy, and that's going to be in terms of the thermometer. We can use the thermometer, get the temperature in degrees Celsius or in Kelvin, but we can measure this. And then we can measure kinetic energy as well. We can measure kinetic energy, and a little bit more difficult to measure kinetic energy than temperature, obviously, but we can measure that and see that correlation. Okay, but again, we can easily measure heat energy and the changes in heat energy by using the thermometer. Okay? All right, very good. So with that said, let me ask you to consider this problem here real quick. Okay, so on your paper, let's just work this one out really quickly together. Okay, so on your paper, I would like you to determine by what factor the average kinetic energy of the sample of helium will increase by if we increase the temperature from 100 Kelvin to 200 Kelvin. So go ahead on your paper, take about a minute to get this done. I don't think it should be too long for you. If you write that out, and then let's see what you come up with. Okay, so by what factor does the kinetic energy increase? Okay. Okay, let's go ahead and take a look at this, folks. Again, I don't think it should have been that difficult for you. Let's go ahead and take a look at this. Okay, so we have a gas. The gas here is helium. It starts out at a temperature of 100 Kelvin. Okay, and then we increase that temperature. We increase the temperature. That means we add heat. Okay, we're going to add heat energy. So we increase the temperature here. All the way till we get to 200 Kelvin. Okay, so we add enough heat and take a second measurement, and the temperature increases to 200 Kelvin. Okay. The question then is, we don't know what the exact kinetic energy is. We don't know that. We're not told that at all. But we're just asked then by how much. First of all, recognize that it does increase. Okay. Okay. So we know that it changes. If we add in heat energy here, we know that the kinetic energy changes. The question is, and that's what they're asking you then, is by what factor? Okay, by what factor? How much does it change? Okay, does it increase or decrease? Well, first of all, we see that there's an increase here, and that is, we see then that the temperature doubles. Okay, so if the temperature is doubled, then we can, because the temperature is in Kelvin. Okay, so make sure you check that. That's the only thing you got to be mindful of. And since the temperature is in Kelvin, the kinetic energy will also double. Now, if I had given you this in 100 degrees Celsius to 200 degrees Celsius, then the relationship will not be as clear cut as this. Okay, so you got to make sure, if you're given the temperatures here, so if you're given these temperatures in degrees Celsius, for example, okay, so we were talking about 100 degrees Celsius and to 200 degrees Celsius, to determine by what factor the kinetic energy increases, you have to convert that into Kelvin, which would be 373 here, 373 Kelvin, and 473 Kelvin here. So add 273 to each one of those, okay? All right, so that's what you want to make sure you do before you do that comparison, okay? All right, very good. Let me go ahead then, and I'm running a little long time. Let me go a little bit over here just to wrap things up a little bit, okay? So let me go ahead and wrap things up here. Tomorrow, what we're going to do then, so with gases, what we see there is that gases behave, they are a unique state of matter that we will spend more time studying in chapter 14, okay? They are a unique state of matter in that we rely on gases. Gases are absolutely important. In the absence of a gas, like, for example, deep space, it's very hard to sustain anything, okay, because there's no pressure. And so the gas pressure itself is a very important property of gases. And what we're going to do in chapter 14 is that we will go ahead and we're going to study that property much more closely. And we're going to talk about then how the gas pressure is related to other factors that affects the gases as well, and that's temperature and volume. Okay. And so with that said, please make sure you keep in mind then that there's a couple of things from the first section here that you really got to make sure that you can hammer home. That is how pressure is formed on the microscopic level. What are the gas particles doing that leads to the pressure that we can experience between them? And then make sure then you can make the connection between energy and pressure itself. Okay, and so we talked about kinetic energy and temperature and how they're related and how those two will relate to pressure. And so I will get back to that discussion in chapter 14, but make sure you really understand that as we move forward. What you have noticed so far, I think, in chapter 13, I hope, is that this is all conceptual stuff. And like I pointed out to you in class, folks, conceptual concepts are very difficult to wrap your mind or to learn, because there's no practice, there's no repetitiveness to it. What the repetition here comes in, just trying to toss these ideas around in your mind, trying to make those observations or trying to make connections to what you think you understand about those concepts, and try maybe to connect to real life things that you see around you, because that will help. Okay? That definitely helps to be able to find things around you in your everyday life that will allow you to better understand those concepts. But outside of that, unlike the calculations, there's no way that you can repeat and practice this and write it out. Okay. And so make sure you come by and see me, folks. And that's why it's important. And unfortunately, with the circumstances the way they are, it makes it more difficult. But make sure you make that effort to come by and see me and confirm with me what you believe is correct. And I will either say, yes, that's absolutely right, or I will help you kind of get to the point where you do. I'll guide you in the right direction to help you better understand those concepts. Okay. And so moving forward, folks, we only had one calculation in this chapter, and that was a fairly easy calculation involving pressure changes. So moving forward, folks, everything is going to be conceptual. So you have to make sure you come by and you see me and get that extra help with it. Okay, so the section on liquids, the section on solids is all conceptual. And so make sure you come by and see me. And we're going to go through this section fairly quickly tomorrow and hopefully Friday. But so please make sure you take a look at it, and make sure you take a look at evaporation, vapor pressure, and boiling point. You make sure you understand what boiling point, then how it changes with atmospheric pressure. And so if you take a look at these early, take a look at these before we talk about them tomorrow, I can go through them a little bit more quickly. Okay. All right, folks. So very good. I will see you hopefully either today after school or tomorrow in lecture. Okay. All right, folks. I will talk.